Dear students of Vocational Training Diploma on Electrical and Hybrid Vehicles, I am Engineer Mohammed Masad from the University of Jordan, member of EcoCar Committee under the Erasmus Plus project coordinated by the University of Jordan. Still, we are in cluster number 5 about basic of electricity and electronics. Dear students, welcome again in lecture number 2 of topic number 2 about basic of electric and electronic components. This second lecture of topic number 2 will be about 50 minutes and will cover the following chapters. Electrical transformers, capacitors, which belongs to the passive electrical components, and then we will continue in active electronic components. This subject, which is electrical transformers, as in chapter 3, this chapter will cover a brief introduction of electrical transformers. What is it? The construction of a transformer, its function, classifications of transformers, and turns ratio of transformation with some examples and problems. Introduction about electrical transformers. A transformer is an electrical device which transfers the electrical power operating at a particular current and voltage of one circuit to the other circuit, which is operating at different current and voltage levels. Most of the transformers are manufactured such that their characteristics must match for special application requirements such as constant current and constant voltage. Most common types of transformers found in electronic applications include power transformers, instrument transformers, auto transformers. Definition of electrical transformers. A transformer is a device that works with alternating current to transfer electrical energy from one alternating current circuit to one or more other circuits, either increasing stepping up or reducing stepping down the voltage, or to convert the alternating current with a specific voltage value into alternating current with another voltage value without changing the frequency. As you see, this is the shape of the transformer. We have here the primary circuit and we have here the secondary circuit, and this is the core. So this is also the symbol of transformer. We have here the input, this is the primary voltage, and this is the secondary voltage, and we have the magnetic core. So we have here alternating current, and also we have here also alternating current. It is step up or step down the voltage with the same frequency, the input and the output. So we have here input with AC, and we have here output also with AC. So this is the division of electrical transformers, which have input and output, and use the alternating current in the primary side and the secondary. Transformers construction. The transformer consists mainly of a primary coil, as we said in the last slide, a secondary coil, and an iron core that passes through each coil as follows. So we have here, this is the transformers, we have AC signal, and also we have here AC output, This is the secondary current. This is the secondary voltage. We have AC to run this load as an example. This is a lamp. So this is the construction of the transformer. Coil of insulated copper wire whose ends are connected to an AC power source. This is the power source. One of them is connected to the electrical power source. This is the primary source and is called the primary winding. This is the primary winding and consists of a certain number of winding NP turns. So this is how many turns for the primary is called NP. This is primary winding. The second coil is a secondary winding. This is the secondary winding of an insulated copper wire whose ends are, this is two ends, connected to the AC load, which the power is to be connected. It is called the secondary winding. It also consists of certain number of winding NS. So we have here NP for the primary, and this is NS for the secondary. How many turns in the input on the primary, and how many turns on the output of the secondary circuit or coil. Classifications of transformers. Transformers are classified into two types based on the conversion of voltage level. These are step up and step down transformers. This is many different kinds of transformers. Maybe this is a step up or step down transformer with these primary windings or secondary windings as you see. When a transformer is used to increase the voltage on its secondary winding with respect to the primary, it's called a step-up transformer. But when it's used to decrease the voltage on the secondary winding with respect to the primary, it's called a step-down transformer. So the step-up transformer increase the voltage on the secondary winding, and the step-down transformer decrease the voltage on the secondary winding. Principle of transformer. A step-down transformer compares high voltage with low current into low voltage, high current power. So this is step-down transformer. This is the primary windings. This is more turns than the secondary windings. So this is a step-down transformer. Step-down transformers to decrease the input AC input voltage to another output AC voltage. This is E1 voltage or V1 or E1. This is E2 or V2 voltage. So this is T1 stands for the number of winding of the primary, and this is for the T2. So step down transformers, low turns for this side, low voltage, high current. A step up transformer converts low voltage instead of high voltage here, and high current instead of low current in step down transformer to high voltage instead of low voltage here, low current instead of high current on the secondary coil of the transformer as we see here. So we have low voltage, input low voltage on the primary. We see here more voltage at the output. Since we have here the number of turns here is less than the number of turns on the secondary winding. So this is increase the number of turns, increase the voltage, but decrease the current. So this is a stepped up transformers with many turns. You see here, many turns on this side, high voltage. This is, you see, this is low voltage. This is high voltage E2, more voltage than this one, AC, with low current on this side. Definition of turns ratio, TR. Turns ratio value dictates the operation of the transformer, and the ratio of the primary to the secondary, the ratio of the input to the output. This ratio gives us the relation between the number of turns of the primary coil divided by the number of turns of the secondary coils as shown in the below equation. Turns ratio TR equal N. It's equal to the primary voltage, as we see here. This is the input voltage to the primary, VP, divided by the secondary voltage. This is the secondary voltage. Also equal number of primary windings, NP, divided by the number of coils of the secondary, NS, and also equal to the secondary current here, secondary current, divided by the IP current, primary current. See here, VP is the primary voltage, IP the primary current, Vs secondary voltage, Is is the current in this secondary coil, Np, this one, number of primary winding, and Ns is the number of secondary winding. So turns ratio equal Vp over Vs divided by Vs, but for the current, the secondary current divided by the IP, the primary current. Let's take an example, number one, about turns ratio. According to the figure, this figure shows about a step-down transformer. This transformer have an input of 120 volts with 1 amps as an input, with 12 volts, 10 amps as an output. So this is step-down transformers. Step down the voltage from 120 to 10 and increase the current from 1 amps to 10 amps on the output. So if the primary coils is 100 turns, so if we have here a 10 turns on the secondary coils is 10 turns and 100 turns on the primary. So what will happen? So it's here 100 turns, 10 turns, Let's see. The voltage induced in the secondary coil will be reduced by factor of 10. So we have here 120 and here 12. So it is reduced by factor of 10. So 120 divided by 10, it is about 12 volts. So this is a step down transformer of the voltage. So it's from 100 to 12 volt AC. In this case, the transformer is a step down transformer as the primary voltage is 120 and the corresponding voltage is lower at 12 volts. So this is an example of a step down transformer. Let's take another example for a step down transformer. We have 120 volt as input primary voltage. We have here 60 voltage the secondary. We have here 1000 tens, 500 tens. So 1000 tens divided by 500 tens. So we can get the tens ratio as we see here, this equation. So tens ratio 1000 divided by 500 equal to, it means that there are two primary winding for every one secondary winding. The output secondary voltage 100 divided by 2 equals 60 volt. See here, this one, tens ratio equal NP VP over VS. So this is 120, this is 2. So VS equal 100 divided by 2. So we can get the output voltage or the secondary voltage. So as you see here, the ratio moves from large number of the on the left, a large number, to a small number to the right. So the primary voltage is therefore a step down in value. Let's take another example, but instead of step down transformer, let's see what about step up transformer. See here, a voltage has 10 turns of the primary with 10 turns of the secondary. We have here 1000 volt, 4 ampere, and with 10 turns. Okay, what will be the turns ratio in this case of the transformer, and what is the secondary voltage by using the equation of the turns ratio corresponding to the voltage and current. This is the equation. So turns ratio equal 10,000 divided by 5,000, so it is 0.2, which means that there is one primary winding for every 5 secondary winding. So this is step up of number of coils, number of turns of coils. It means step up transformer, and also step up for the voltage. But you see here is the step down of or decrease the current from 4 ampere to 0.8 ampere. So the output secondary current is 0.2, the output 0.2 multiplied by 4 is 4 ampere multiplied by the turns ratio equal 0.8 ampere. It's 0.8 ampere. As the ratio moves from small number on the left of turns of the coil and also of the small of voltage, the primary voltage is therefore step up in value from 1000 5000 volt. I want to talk about the fourth components of the passive components, which is called the capacitors. Uh, this chapter of capacitor will cover several topics, includes a brief introduction about electric capacitors. What is it? The construction of a capacitor, its function, types and classifications of capacitors. In a practical lab, you will see how to teach, how to measure and check the capacitor by using multimeter. Definition of capacitance: the amount of electrons stored in capacitor is known as capacitance. Capacitor is two-terminal passive component having property of capacitance. For example, this is shape of another kind of capacitors called electrolytic capacitors, and we will give more information about this kind of electrolytic capacitor. We have here this is the capacitance. It's about 1000 microfarad, and the working voltage of this capacitor is 63 volt. So the why we use the capacitor? It used to store energy in the form of electrical charge for a period of time and retain store energy to other circuit components. So this benefit of this capacitor is to store energy and return this stored energy to another circuit components. More the capacitance, more of the capacitance means more in capacity to store charge. It's like a tank of water. More size of tanks means more water to store inside these tanks, like the same of capacitors inside. The unit of capacitance is farad, F, and usually capacitor is used in microfarad to picofarad. Construction of capacitor. It consists of two conductive plates, like this, two plates here. Each plate carrying an electric charge of equal magnitude and opposite sign. The electric charge is then used up or dissipated in time. So these two plates, which the construction of the capacitors, this place one goes to the positive part of the battery, and this is the negative part of the battery. So we have here positive charges and we have here negative charges, okay, and there is insulator inside this capacitor, okay, and this is the main function of the capacitor is used to store of charge or stores of energy, okay. This is the symbol of capacitor. This is the positive and this is the negative terminal of the capacitor. Schematic symbols for capacitors. There are many types of capacitors that can be categorized into two major groups. One is called polarized capacitors and the other is called non-polarized capacitors. Sometimes if we see a ceramic capacitor, it is non-polarized capacitor. Electrolytic capacitors and tantalum capacitors are polarized. As you see in this figure, this is a ceramic capacitor and this is electrolytic capacitor. So it is non-polarized and this is polarized. So this is the positive, the tall one, polarized lead, okay, and this is the negative lead of the electrolytic capacitors. So this is polarized, this is non-polarized capacitors. This is the symbol of the non-polarized and polarized capacitors. This is non-polarized, this is polarized capacitors. We have here the positive, and this is the negative terminal of the capacitor. Capacitor types also. The type of capacitor is determined by the insulating material between the two plates of the capacitor used in its manufacture. The capacitor is called a mica capacitor if the insulating material is mica, but if the insulating material is ceramic, the capacitor is called a ceramic capacitor. If the insulating material is a chemical solution, the capacitor is called electrolytic capacitor. Types of electrolytic capacitors. These kind of capacitors are polarized, as we mentioned last slides. It's used in power supplies and usually above 1 microfarad. This is many kinds of electrolytic capacitors. This one, this is a small one, this is small. This is another shape of the electrolytic capacitors. So this is a polarized capacitors with negative part, and this is positive part. This side is the negative, this is the positive. It is also here another kind of electrolytic capacitors. So you see here small size of capacitors. We have here a big size of capacitors. So more size means more capacitance. It's more to store energy or more to store electrons or charges. Sorry. Electrolytic capacitors, as we see here, nowadays in automotive vehicles and hybrid vehicles like Prius, we can see electrolytic capacitors in the inverter converter unit, which belongs to the high voltage system in the Prius. We have here huge capacitors, about 2,500 microfarad, 450 volt, like this. This one, Toyota, manufactured by Panasonic. It's about 450 volt, 2,700 microfarad. This is very dangerous capacitors in the inverter converter unit in a Prius. It is used to store energy. This is one of the units used in the inverter converter unit in the Prius, the inverter converter unit Prius. Okay, which is 450, 2050 microfarad, and this is the inverter converter in the Prius. Very high voltage here. You see, this is the orange cables, means high voltage go to inside the inverter converter from the high voltage battery. Now there is a new technology of capacitors used to store energy. It is called supercapacitors. You see here, this is 1000 farad, 2.3 volt. This is new technology used in electric or hybrid cars to store energy, to more to decrease the size of the battery, to store more energy. So this is the new technology of manufacturing of capacitors. So this is larger capacitors. 1 farad equal 1 million microfarad with the small size of the capacitor. 1000 farad, see here, is a huge value of microfarad. So cylindrical or electrolytic capacitors, the chemical capacitor has very high capacity and low voltage. You see here, this is low voltage but high capacitance. According to the working voltage of the capacitors, the electrolytic capacitors, this is electrolytic capacitor. Here is the working voltage, is about 25 volt, and here is the capacitance, 4500 microfarad. This is the positive lead and this is the negative lead of the electrolytic capacitor. This is high capacity with low voltage. High capacity, low voltage. But if we see here, we have here low voltage, low capacitance, 22 microfarad, high voltage, 450 volt. See here, 25 volt, low voltage. You have here 450 volt, it's high voltage. But you see here, low capacitance with high capacitance here. What is the relation between electric charge and capacitance of a capacitor? This is the triangle. In this, you can see the formula between the charges and the capacitance and the voltage of the capacitor. Okay, this is capacitor. This is the plus minus plates of the, and this is the voltage. So what is the relation between these? Q, this is stored electric charge measured in coulombs, and this is the voltage on the capacitor measured in voltage, and this is the capacitance of a capacitor is measured in farad. So the more store energy, more electric charge, it depends on the voltage and on the capacitance. So more farads means more store energy in the capacitor. This is the formula between the charges, how to store energy, comparing to the capacitance of the capacitor and to the voltage. Units of capacitors: farad, millifarad, microfarad, nanofarad, picofarad. Farad is equal or multiplied by 1 is microfarad. 10 minus 3, 2 minus 6, nano 2 minus 9, pico 2 minus 10. So 1 farad, 1 farad. For example, here 12 microfarad means 0.012 farad. 12 microfarad, 0.0012 farad, 10 nanofarad, 12 nanofarad. You see here is very, very small of farad. we go from macro to nano to pico, it means small of capacitance of the capacitor. 1 farad equal 1 million microfarad. 10 nanofarad equal zero point 0.0 microfarad. 220,000 of picofarad equal 20 nanofarad equal 0.22 microfarad. Formula for series capacitors. As we mentioned before, we can use multi or many of the resistors in series or in parallel. So also many capacitors can be in series or in parallel circuits. So what is the comparison between these series capacitors according to the series resistors, as we want to see like this? Connecting capacitors in series decrease total capacitance, but in series of resistors, the total resistance increased. Here is decreased. Same as connecting resistance in parallel. So series capacitance the same in resistors in parallel. The working voltage is sum up of each capacitor voltage, as shown in the example below. We have here now two capacitors in series. So the equivalent or the C total for these two capacitors in series is equal C1 multiplied by C2 divided the sum. You know this? This is the same of the resistors in parallel. For example, we have here two capacitors. One is 10 microfarad. This is 10 microfarad. This is polarized. We have here 50 volt. This capacitor is for 50 volt. This is the working voltage of this capacitor. So what is the equivalent of this or the total of the capacitance? See, 10 by 10 divided by 10 plus 10. So 10 by 10 divided by 20, it's what is 5 microfarad. This is the C total of these two capacitors. The working voltage now is sum up of each capacitor voltage. So since here we have two different voltages for different capacitors, so the working voltage equal the sum, which is about 700 watt. Formula for parallel capacitors. Now we have here parallel capacitors. The formula for this is the same for resistors in series. So in capacitors here in parallel, same as connecting resistors in series. So it is increasing the capacitance as you see in this formula. Okay. So we have here four capacitors in parallel. So the equivalent capacitor or here is C total equal the sum of these capacitors C1, C2, C3, C4. Let's take an example. We have here a circuit of three parallel of capacitors 5, 10, 15 microfarad. So according to formula, as the same of resistors in series, we sum these capacitors. So C total equal 5 plus 10 plus 15 microfarad is equal 30 microfarad. Let's take another example. We have here also three capacitors in series with different working voltage. So what is the capacitors here? The C total. C total here is 1 microfarad plus 2 plus 1. So it is 1, 2, 3, 4. 4 microfarad. What about the working voltage? The working voltage for this circuit is the lowest voltage, the combination. Okay, so it is 100 volt. This is the working voltage for these three capacitors. Now, active components can be classified into mainly two types: electronic diodes and electronic transistors. But also there is also logic gates, and also there is integrated circuits, ICs. But later we can discuss and give some information about these for more high levels of students, but not in this topics. Now, definition of diode. Diode is one-way valve for electricity. It's like a switch, okay, or valve. It's a two-terminal semiconductor like this. This is shape of the diodes. See, this is the symbol of the diode with two terminals, and this is the shape also for the diodes. We have here, this is the positive side, is called anode, and this is the negative side, which is called cathode. And here, this for the black diode, we have here a white area. This indicates for the cathode or the negative part of the diode. So these diodes leave the electricity to flow only in one direction, in this direction, from this side to this side, from the anode to the negative side, or from the anode to the cathode. This direction, flow of current from the anode to the cathode, or from this side to this side. But you see, this is like a valve or a switch. It permits the flow of current from this side, but it prevents the current to go on this side. So it looks like a switch, and this side is closed, but on this side the switch is open, so there is no current. So this is the positive, and this is the negative side of the diode. It's usually come in a glass or a plastic cylindrical package like this. This is maybe plastic or maybe glass, and also there is some indication here or marked with a strip to indicate the polarity of the side of the diode. Most of them used to indicate the cathode, the minus terminal. Now, definition of transistor, the second type of active components. Transistor looks, its function is like a water tap. This is, as you know, a water tap is used to prevent the water from this side to this side by controlling of this. Okay, so it's like a valve also, it's like a switch, but there is a controller of this switch. So the transistors shapes like this electronic transistor. You see here is three terminals, and then also water type is in, out, and this is the control part of the water tap. So transistor is, as you see here, it's a three terminals semiconductor. This is semiconductor device, which a voltage is applied to one of the terminal. Here is the applied of voltage here, to control the flow of current. This one can control the flow of water, but in electronic transistor like this, the voltage to the base control the flow of current from the C to E side or E terminal. So the transistor, as you see here, has three terminals. It's called emitter, base, collector. This is transistor symbol, and you see here, this is a transistor. We have three terminals. One is called emitter, the second terminal is called base, and third terminal is called a collector. And this is the symbol of the transistor here. It's like this one. Okay, this is the base, and this is the collector, and this is the emitter. Symbol of transistors. Okay, there is two types of transistors. One is called NPN transistor and PNP transistor. Both of them has three terminals: emitter, collector, and base. See here, this is three terminals. One base, this one is the base. This is the second one is collector. This is the they call emitter. So if you see here the transistors inside, we have two diodes inside the transistor. So this diode, this transistor is called NPN transistor, and this one, if the direction of the diode like this, is called PNP transistor. See here, this is PNP transistor like this one. You see the direction of this diode like this, and this is the NPN transistor like this. You see the direction of this diode like this one. So this is one. This is called NPN transistor, and this, so P, this is the base, N is the base here. So this is NPN, NPN, and this is PNP. So the middle is the base of the transistor. Function of a transistor. Transistor has very fast response and is used in a number of functions, including voltage regulations, amplifications, switching, oscillators, etc. Transistor may be packaged individually, or they can be a part of an IC, integrated circuit. You see now the very important function of the transistors. It's used inside the integrated circuits. Some also of IC, you see here, have billions of transistors, which is in a very small area. So this is a very fast technology of manufacturing of integrated circuits by using billions of transistors inside it. Now this is the reference for this topic number 2. You can follow, you can read, you can visit these links to get more information about this topic of components, which is the active and passive components. Thank you for your attention, and also thank you, and any questions I am ready to answer.